Chiara, welcome to SwissMap. So Chiara Saffirio is one of the new group leaders, and he will be representing the highlight of the quantum systems projects of the year. So Chiara, I give you the floor.
Thank you very much for the introduction. The work I want to present you today is related to the quantum system project, and it inserts in the more general framework of deriving an effective evolution equation starting from many-body quantum dynamics. And here is the general picture of the kind of problem I want to look at. So you have n quantum interacting particles. And so at a microscopic scale, their evolution is described by the many-body Schrödinger equation. So you have a wave function, and this wave function depends, of course, on time, but also on the n positions of the n variables. And the problem here is that the number of particles, so this capital N, is typically a huge number in the kind of systems that we want to model. And therefore, it's very difficult to extract physical useful information from this many-body Schrödinger equation. So the whole goal is to pass from a microscopic picture to a macroscopic one through a scaling limit of some sort to get an effective dynamics in which instead you have only one unknown that somehow encodes all the informations you want to look at. And for the aim of this presentation, I will speak about the Vlasov-Poisson equation as an effective dynamics. So this step from microscopic scale to macroscopic scale is usually referred to as the derivation problem from n-particle system. So let's go to the setting of the problem I want to present you. So we consider a system of n interacting fermions and the associated Hamiltonian to it, that is, as usual, made of a part which is related to the kinetic energy, a part that is related to the potential energy. Here the potential is this capital V. And then we have also an external potential that is there just to trap the system in a volume of order 1. And this lambda that is here highlighted in red, that is a coupling constant. So the thing I'm interested in is the dynamics, so I want to switch off the external potential to see how the system evolves in time. And of course it does following the many-body Schrödinger equation. And the study we want to perform is to look at low energy states and look how they evolve in time. So in general, this equation is simple because it's a linear equation. So you know, for example, that the solution exists, is unique, but you don't know anything more because of the n that is a huge number. And even if you plug this solution into a computer, then it will take forever to get some information because of the high computational cost. So this is the picture. So we want to look at a certain regime that we want to identify in order to see if there is an effective dynamics that approximate well enough this system. And for this presentation, the regime I want to look at is the fermionic mean field regime. And this works as follows. So we have this coupling constant lambda, and we want to choose it or scale it in such a way that the two terms of the energy for this system have the same size. And this results to be when lambda is n to the minus 1/3. This is at least in dimension 3, but it's much more general. So it's going to be 1 over the dimension of the space. So this is the first scaling we do. And then on the other hand, we also want to somehow be able to follow the evolution of our system on a time scale of order 1. So we also rescale the time variable in order to look at time scales of order 1. And what it results from this scaling is that we have a many-body Schrödinger equation in which now we have a dependence on the number of particles in certain places. And one place is here in front of the kinetic part of the the interaction part of the Hamiltonian, that is the usual 1 over n for the mean field. But then there are also some dependence on n in front of the Laplace operator and the time derivative. And I've called it here epsilon, but you see this epsilon is linked to the number of particles. And the observation is that this epsilon is placed in the exact same place where usually the h bar is, the Planck constant. And this means that in the particular case of fermions, the mean field and the semi-classical scaling are naturally coupled. So the question I want to address then is the following: what happens when we take the number of particles which goes to infinity, that models the fact that we have many particles? Can we get an effective dynamics out of it? And this is a very, this problem has been studied quite extensively. And the first results goes back to Narnofer and Stuel in the 80s and to Spohn. And what they proved was that when you have very regular interaction potentials, then you can indeed perform this limit and approximate the many-body Schrödinger equation with the Vlasov dynamics. So what is the Vlasov equation? Then is a nonlinear PDE in which the unknown is a probability on the phase space. So it's a density function on the phase space. And so this is like a direct limit. So you take n which goes to infinity and immediately you get both mean field and semi-classical at the same time. So it's a very good and a nice result. On the other hand, the drawback is that because of the techniques, we have two limitations. One is that potentials have to be very smooth. And in many applications, we want singular potentials. For example, if you want to model atoms and large atoms and molecules, so you want the potential to be the Coulomb one. And the second drawback is that the method doesn't allow for explicit estimates. That is something that we really like to for applications, because we want to see how big should n be in order for this approximation to be a correct one. So there is another approach that is the one I want to, that is related to the result I'm gonna present. That is, well, we can do it in two steps. We can first take n sufficiently large and approximate the many-body Schrödinger equation with the Hartree-Fock equation, that is an equation for the operator omega, that is the one particle reduced density matrix. So this is again a nonlinear equation, but now we have not anymore the n particle wave function, but the one particle density matrix. So it is the first simplification of the problem in terms of complexity. On the other hand, we can then afterwards take the limit for epsilon which goes to 0, that anyway means n which goes to infinity because of the coupling between n and epsilon, and get again the Vlasov equation. So the advantage of this splitting of the problem is that techniques here allow to get explicit rates. So I've been working in recent years on this horizontal line from many-body to Hartree-Fock, but what I want to present you today is more about the vertical line, so what is more concerned with the semi-classical limit. And this is the content of a very recent result together with Laurent Laflèche from the University of Texas, University of Austin, Texas. And so what we were able to prove is that you can take a very general singular potential. This includes the case of the Coulomb potential, that is the most relevant one from a physical viewpoint. But also you can think of whatever, even non-radially symmetric singular potential, even more singular than Coulomb. This is included in our analysis. And all dimensions, not only d equal to 3. Then we prove that indeed the Hartree-Fock equation dynamics is well approximated by the Vlasov-Poisson equation, that is the Vlasov equation with the singular potential. And this is done in strong topology, meaning that we prove that in trace or Hilbert-Schmidt norm, we have such a convergence with an explicit rate of convergence that depends on this parameter n and epsilon. So one of the two, since the two are linked. Actually, it works for whatever Schottern norms, but the most relevant one for the applications are, of course, trace and Hilbert-Schmidt norms. So the reason why we can go that farther with respect to previous results, in which instead the potential was taken only to be Lipschitz, actually the derivative of the potential to be Lipschitz, is because we strongly use the informations that we have on the limiting equation. So the fact that we know a lot of things about the Vlasov-Poisson equation from the PD viewpoint, like regularity of solutions, propagation of moments. So this is the main new ingredient in our analysis, together with the fact that we consider the problem at the level of operators and not at the level of density on the phase space. There is anyway one restriction, that is the fact that because of the fact that we look at the high regularity of the solutions of the Vlasov-Poisson equation, we need to consider only mixed states, say states that are relevant at positive temperature. And this is really related to the fact that since we want high regularity, we need to impose some regularity also on the initial data. So I want now to conclude with two perspectives. So there are two ongoing works that we are looking at the moment. So one is we would really like to close the graph that I have presented you before. So actually there is one of my previous work together with Marcello Porta, Benjamin Schlein, that is also a member of SwissMap, Nils Beneditter and Eugen Jaksic, in which we proved that for mixed states, this horizontal arrow is actually a good approximation, but it works only for smooth potentials. So in order to close the graph, for instance, for the Coulomb case, we want to look at this horizontal error for singular potentials in the case of positive temperature states. And this is something we are investigating. And the second extension is that one would also be interested in the semi-classical limit for pure states. And that means states that are relevant at 0 temperature. And this is something we are instead looking at with two postdocs in my group in Basel, Daniele Di Monte and Nicolai Leopold.
Maybe one last question. Now that you're back into SwissMap as a group leader, do you have any potential interaction with other groups or within the quantum system project?
So, well, we have interactions with the group of Benjamin Schlein, and well, more than interaction is more like contacts with the group of Gian-Michele Graf at ETH Zurich. Also some interaction with the people in the statistical mechanics group. And so in particular, there is also a recent member, Michaela Jacobelli, who is working on the Vlasov-Poisson equation. And Alessio Figalli has also been working on topics related to kinetic theory. That is another part of my research. So these are, I would say, the main connections that I have within SwissMap, the statistical mechanics group and, of course, the quantum system group.